of physical qubit systems, in particular superconducting qubits, the type that we work with at IBM. And then, so maybe after about half hour, 45 minutes or so of that, then we'll switch to doing a demonstration on the IBM Quantum Experience website. If you have an account there, you're encouraged to follow along with some of the things we'll walk through. And if you have any questions, feel free to raise your hand or post in the chat. Certainly, we'll definitely have time at the end, but I definitely like to sort of, if I'm saying something that doesn't make any it makes no sense whatsoever, I definitely would like to hear it so I can adjust accordingly. So with that, let me go ahead. I'm going to go ahead and share my screen. And,
just sit outside for 5 minutes. Come on.
It's going to share. Okay, and so I assume everyone can see that. The title of this talk is Quantum Computing, Qiskit, and the Quest for Quantum Advantage. Quantum Advantage being the idea that someday quantum computers will let us do things that we can never do with existing computers. And as a starting point in that theme, I wanted to start with talking about this simple molecule here. This is a molecule that is pretty simple. It has fewer than 200 electrons in it. It's made of carbon, hydrogen, nitrogen, and oxygen. It's a molecule that we're all familiar with from our daily lives, and we have a pretty good idea of what it does. It's actually the caffeine molecule. And remarkably, though, if you wanted to simulate the exact properties of this molecule using a computer that exists today, you couldn't do it. It's simply too complicated. And even in principle, if you could build the biggest supercomputer that you could imagine in order to have enough memory and enough processing power to try to understand exactly what's going on and do the exact calculations of the states of this molecule, you'd find that you would need to use, basically take almost all the atoms in the world and use them to make this computer. It would be an obscene amount of, an obscenely sized computer that you would need. And so we consider problems like this to be just completely intractable for computers as they exist today. And if you think about Moore's law, for instance, which you may have heard of, as a sort of a description of the progress in computing over the course of the 20th century, Moore's law was the idea that at a certain predictable cadence, transistors get smaller, they get cheaper, you can put more of them on a chip, you can make computers that are more and more powerful. But what we're talking about here, though, as I just said, is something that, even if you could continue this trend up to the point where you are making computers as efficient as you can possibly make them using the way we currently make computers classically, you'd find that you would just be using an insane amount of resources in order to make such a computer. And so it's just completely not feasible. So what we need is, in order to tackle this problem, is not to just accelerate Moore's law or continue it. We need a whole new paradigm of computing. And so one of the things I want to emphasize about Moore's law and the history of computing until now is that even though these two devices may look very different, right? The ENIAC computer from the 1940s and the smartphone from today, in principle, the underlying model of computation called the Turing model is essentially the same idea, right? You're working with bits that are zeros or ones, and you're doing operations on these bits that are, AND operations or NOT operations or controlled NOT operations. There's a certain set of operations on these bits that operate on individual bits or on pairs of bits. And that model has stayed essentially the same throughout all these decades. What's changing is the underlying technology of how are these transistors made, right, and how are the different pieces put together in an efficient way. But it's still the same paradigm. And so that is what why we're excited about quantum computing. Quantum computing is not just an extension, an acceleration of Moore's law. It gives us a whole new paradigm of computing, a whole new way of thinking about computing that's different from anything that came before it. And that's potentially, and that's why people are excited about it, potentially it has the ability to let us crack some of these problems, like, for instance, the caffeine molecule that I showed, that even if you made the most powerful computer that you could possibly imagine, using traditional technology, you wouldn't be able to solve. And so what is it about quantum mechanics that lets us do this? Well, quantum mechanics, I like to think of it as sort of a two-sided coin. It provides certain resources for us that we can try to harness in our computations. But each of those resources has an associated challenge or drawback associated with it. And so what we need to do in trying to build a quantum computer is figure out how to harness these resources that it gives us, while at the same time managing the disadvantages and challenges that come with them. And so in a nutshell, I'm summarizing all four of them on here. And I'm not going to go into a ton of detail initially, but I hope that by the end of this hour and a half or so, you've gotten a good degree of familiarity with each of these. So just to start off, what are the features? Well, superposition is the idea. You may have heard of the Schrodinger's cat paradox, for instance. It's this idea that a system can be in sort of two different states at once, you might call it. That's sort of a little bit of a sloppy way to say it, but it sort of captures the idea. The idea that, Schrodinger's cat paradox, of course, was the idea that if you have a cat that's in a box and there's a mechanism inside the box that has the potential to kill the cat at some point randomly, well, until you open that box, the cat is sort of simultaneously alive and dead. It's in this sort of superposition of being alive and dead. And until you actually open the box and look at it, it's really sort of in both states, and the act of opening the box is what causes the cat to possibly die or not die, because then you looked at it, you've measured the cat to be either dead or alive. This was intentionally sort of a ridiculous thought experiment. The idea isn't that this actually happens in real life, and the fact that it doesn't happen in real life is part of why quantum mechanics is challenging. We'll elaborate more on this later, right? The fact that things that happen on the subatomic scale, like superposition, are just totally alien to us when it comes to things on the macroscopic scale that we're familiar with from our day-to-day life. It makes it very hard to reason about these systems and understand them. But suffice it to say that experiments have shown, and we'll see later today, that you can indeed put systems that are simple and isolated enough into states that are superpositions of different states, and really see this quantum behavior, where they really act as, you can think of a superposition state as a state it's a definite state, right? But it will behave randomly, in a predictable way. But it will behave in a random way, depending on how you manipulate it. So superposition, is one of the key building blocks of or key features that quantum mechanics gives us. Applied to computing, it's fairly straightforward. With classical computers, we have zeros and ones, and now essentially instead of saying, okay, a bit is either a 0 or a 1, we can now say, okay, we can have a quantum bit that can be some combination of 0 and 1, right? And we'll see more on that later. Entanglement is even a little bit weirder than superposition. This was what Einstein actually called spooky action at a distance. Einstein famously was sort of skeptical of quantum mechanics and many of the predictions of quantum mechanics, at least in particular entanglement. The idea is that if you have, say, two particles that are in some sort of superposition state, even though each of them is behaving randomly, you can get them to interact in such a way that they become entangled. And what that means is that if you entangle them and then, say, separate them by some large distance, even if they're separated really far away, if you then measure one of them, it will instantaneously have an effect on the other one. And so if you now think about trying to apply this to computing, it's really kind of weird and really unlike anything that we have in today's computers, because it essentially says that instead of just having a bunch of independent bits in your computer, if you have quantum bits, you can have quantum bits that are not only potentially combinations of 0 and 1 at the same time, but also potentially entangled in strange ways, so that if you do an operation on one of the bits, you'll actually be affecting the whole system in some way. And so taken together, these two principles of quantum mechanics give us a lot more power, it turns out, to do certain types of complex calculations. And interestingly, in particular, they really are expected to be useful for things related to actually things very much like studying that caffeine molecule that I showed at the beginning. The caffeine molecule is a a small isolated system is one of these types of objects that is actually very much governed by the laws of quantum mechanics. The fact that quantum mechanics is so complicated is what makes it difficult to simulate. And by building a quantum computer, a computer that is also governed by the laws of quantum mechanics, it gives us just the right tools that we need to try to simulate something like that more efficiently. That's just one example, though, that people have come up with where we expect quantum computers to yield advantages. We think that there are other advantages as well, as I'll get to toward the end. But that's sort of a very natural example of how you might use these features to do something. Now, there are challenges, as I mentioned, of course. Each of these advantages comes with a trade-off. And so I'll start with the uncertainty principle, actually. The uncertainty principle, and I've illustrated it here as these two sheep, one of which has sort of a red cross through it. That's the uncertainty principle is a principle of quantum mechanics. In the context of quantum computing, it's often referred to as the no cloning theorem. And if you were around in 1998, which I guess most of you weren't or not, that was when a sheep was first cloned for the first time. The sheep was named Dolly, and they cloned the sheep. And so this is a picture of Dolly the sheep, and it's saying that you can't clone. Anyway, this is an illustration of no cloning. The idea, though, is that although a system can be in a superposition state where it's some combination of, say, 0 and 1 at the same time, as soon as you try to measure it and figure out, well, exactly how much 0 is it or exactly how much 1 it is, you can't measure that. You can't measure that precisely. The only outcomes you ever get from a measurement are 0 or 1, right? And so this makes it impossible to measure a quantum state exactly. And it therefore makes it impossible to copy a state or clone a state, right? So if I give you a qubit that's in some arbitrary superposition state, that's some combination 0, some combination of 1, and I just ask you, okay, make a copy of that quantum state. Well, you can't do it because you can't measure. If you just try to measure it, you'll just get 0 or 1, and so there's no way that you can actually copy it. And that is challenging for lots of reasons. I mean, a main reason that this poses a challenge is that if you want to, say you're worried about errors in your system, right? Errors are a problem even in classical computing that's handled at such a low level of hardware that we typically don't even worry about it usually, because it's very simple to correct errors in a classical computer. You can just make a copy of a bit. If you're worried that, say, there's some sort of stray cosmic ray that's going to come in and flip one of your classical bits, well, you can just have 5 copies of that classical bit and do the same processing on all of them. And then, if you notice one of them slipped, just sort of go with the majority of them and ignore the one that's bad. But if you can't make a copy of a quantum bit, then you can't just do error correction as easily. And so that makes error correction a big challenge for quantum computers that we're working on. And then the other challenge associated with quantum computing is decoherence. And decoherence it's sort of related to entanglement, I like to say, in the sense that say you have a quantum computer, which is a collection of quantum bits, all intended to be operated together in a certain way. Well, there's, as far as the universe is concerned, there's nothing special about your quantum computer as opposed to anything else that's around it, right? And controlling entanglement and superposition precisely is very difficult. And so your quantum computer is going to want to just interact with the stuff that's around it. I think that's a pretty intuitive idea, right? You can't if you make it completely isolated, well, then you can't send data in and out of it. So then that's kind of useless. So the second you have a quantum computer that can talk to the outside world, it can also become entangled with the outside world in ways that maybe you didn't intend. And that leads to decoherence. Essentially, what it essentially refers to is the fact that over time, if you say you have a system that you put in a certain quantum state, whether it's a superposition or an entangled state, over time it will drift away from that intended state, and the quantum behavior will sort of be washed out, or you will lose track of it, and that makes it hard to do computing. Imagine if you have a computer and you want to put your bits in a 0 or a 1 or some well-known state, but after some amount of time, well, you don't really know if your bits are 0s or 1s anymore. That poses a challenge. So those are some of the challenges we're working on in the context of quantum computing. With that as motivation, let me just take a quick pause there. I just want to see if there are any like burning questions based on any of that so far. If anyone, let me see how to trying to see how to look in the chat. Oh, I do see a question in the chats. This was back earlier. When I say simulate, do I mean find the ground state of this molecule or how it would interact with other molecules? Yeah, I mean, sort of all of the above, right? It's you know, what are the exact distances between and angles between all of the atoms in the molecule, for instance, right? And then you know that's sort of step one, and then step two would be yeah, how exactly do reactions proceed? I'm not a quantum chemist, so it's you know it's not exactly my you know what I do. You know, I'm not the best person to answer that question. But you know, suffice to say, people are very interested in trying to model this and other molecules for, say, for developing new drugs, for instance, developing new vaccines. Even you can imagine, if we could really understand very well at a molecular level how molecules interact with each other, it would help accelerate a lot of different strains of research. And how do I entangle quantum particles? That's a good question, and I'll come back to how we actually generate entanglement. When it's something that's a little bit hard to describe in the abstract, but when we start to talk about things a little more physically, we can talk about how we generate entanglement. And yeah, challenge of decoherence. Yeah, decoherence. Exactly. It's a lot of it has become because quantum computers can't be that well isolated or as well isolated as they need to be in order to prevent decoherence. And yeah, as far as the idea of the capacitors for retaining charge, yeah, it's a similar idea, but again, I think with trying to do the same thing for qubits, you know, with a traditional bit, you know, you can sort of look at the voltage and see that it's starting to decline and maybe getting close to some threshold, and then you could you know say try to you know, apply a larger voltage to put it back at the right state. We can't really do that with qubits, although there are some ideas that are sort of analogous, and I won't get into it now. I won't get into it too much right now, but we'll save that for later on. So let me keep going for now. These are good questions, and I think it shows that you're all really sort of engaging right where I expect you to be. Just a qubit is not necessarily always in a superposition state, right? If you when you start your computation, you actually just want to start it in the zero state, but then the idea is that you manipulate it to be a superposition state. And you know, a lot of your computation happens when all of your qubits are in superposition states. And then at the end, you measure it, and then when you measure it, of course, you collapse it back down to one of the classical states, 0 or 1, that are not in superposition. And you know, while it's in a superposition, there's sort of there's a whole continuum of superposition states, as we'll see. They sort of one way of thinking about it is as the surface of a sphere, and that the whole surface of the sphere represents different possible states of a qubit. So yeah, these are all really great questions. I'm really glad to see these, even though I can't. I want to keep moving on rather than really go into detail on each one. And I think some of what I'll say a little bit later will help address some of these. But I'm glad to see these types of questions that I think it's just you're really understanding pretty well. So let me get back to the slides. So okay, so we've talked about qubits in the abstract, right? But now, okay, now let's if we try to get practical and think about, well, what should a quantum bit look like? Classical bits, we're familiar with. There are lots of different ways you can represent a classical bit. It's just a 1 or a 0. Lots of different things can represent a classical bit. You know, some of the ones that are used in actual computers are, say, capacitor, the charge on a capacitor, you know, the state of a transistor, you know, a magnet's polarization. If you're in the very early days of computers, people used punch cards where the presence or absence of a hole would represent the 0 or the 1. So lots of different ways you can represent classical bits. It's pretty simple. Quantum bits, it's obviously much trickier. You know, we don't really have examples of systems that behave quantum mechanically in our everyday life. And so the systems are necessarily a bit more exotic. Sort of the simplest system you might think of that could represent a quantum bit is actually, if you think about a single electron, it has a property called spin. And what that means is the electron can be thought of as a little magnet, essentially. And it's a little magnet that can be, have its north pole pointing up or pointing down. And those states are referred to as either spin up or spin down of the electron, and that's sort of the only degree of freedom that this electron has. So it's a very simple system. It has only two allowed states, and it's it can be very well isolated, and it behaves according to the laws of quantum mechanics, as everything in the universe does, right? It's sort of remarkable. Everything around us is behaving according to these rules of quantum mechanics with superposition and entanglement. But in our everyday life, because we're in this limit where we're at very warm temperatures, although it even when it's cold outside, right, it's still, if you talk about, say, the Kelvin scale, we're still much, much warmer than absolute zero, right? So there's a lot of just thermal energy bouncing around, and we have billions and billions of atoms around us, right? And both of these things tend to sort of wash out these quantum effects. But if you go down to something like an individual electron spin, you can isolate that and manipulate that carefully, you'll really find that this is an object that will exhibit superposition and all these other quantum mechanical features. And so the electron spin is sort of, in some sense, nature's perfect qubit. It's just a simple two-level system, and just like you would need to make a quantum bit with 0, 0, or 1. In practice, that is in fact one system that people are pursuing in order to try to make qubits, and I'll come back to that more. But there are certain challenges in working with electrons. I mean, for one thing, they're very, very tiny, and you need some sort of a host medium to, something to host them in, right? You can't just have them floating around. So people have also looked at atoms. Atoms also have, very small numbers of allowed states, and they're a little bit easier to work with than individual electrons. But you're again sort of confined by what nature gives you in terms of what atoms are available, what are the allowed states, what types of energies do they need to work with, what type of equipment do you need to control them. Well, that's you're sort of limited by what you are given by nature. What we work with at IBM and what many people in the field work with are actually superconducting circuits. And these are much, much larger than anything that, any individual atoms or electrons. But remarkably, they actually can be made to behave very similarly. They exhibit a lot of the same properties if designed carefully as, say, individual atoms. In fact, they're often called artificial atoms. And so that's what we're working on at IBM. And I'll go to the next slide and talk a little bit more in detail about some of the different approaches and their alternatives, the trade-offs between them. One thing I just wanted to show on this slide in the lower right is something called the block sphere. And the block sphere is what I was alluding to a minute ago. It's a way to represent superpositions of a single qubit, essentially. So in the block sphere picture, the zero state, which we write with this funny, let me annotate here. So if you see, I'm gonna change the, how do I change the color of my drawing? Huh. Oh well, I was gonna try to draw something, but it's coming out as white, so you can't really see it. Anyway, if you see this zero with the funny bracket around it up at the top here, that's how we write a quantum state, right? To distinguish the quantum state zero of the quantum bit from just the number zero, right? So a quantum bit has two classic, two states that are sort of equivalent to the classical 0 and 1. They're written with this bracket around them, with the 0 at the north pole of the sphere and the 1 at the south pole of this sphere. But then any other point on the surface of the sphere is an allowed state of this quantum bit, but it's a superposition state. And so depending on where exactly it is, if you measure it, you'll either get it 0 or 1, but the likelihood of measuring 0 or 1 will depend on where exactly you are on the surface of the sphere. And that's going to be true regardless of what type of approach we're taking to make the qubit physically. The fundamental underlying behavior is going to be equivalent and described by this block sphere picture. So let me keep going here. Let's clear that. There. So just to talk a little more. Oh, my annotation is still there. I got to get rid of that. There we go. Just talk a little bit more about some of the different physical systems that people are studying to try to realize qubits. You know, I mentioned electron spins. Those are right in the center here. Challenge there is actually that they're very tiny. You need some sort of host material, and then in that host material, it has to be very, very uniform. And then you have to get the signals in and out. And the electrons are so tiny compared to, say, the size of wires that are carrying the signals in and out. It sort of creates a mismatch. You know, if you think about you know, a wire, right, which is sort of on the order of maybe a human hair width, you know, that's sort of micron scale. And then you think about an electron, which is a point particle, it's sort of almost infinitesimally small. It's many, many orders of magnitude smaller than that. And so if you're trying to work with a single electron and trying to send signals to it and then couple individual electrons together, it creates a challenge in terms of the wiring. But people are working on that, and it certainly is an interesting approach and one of the oldest approaches to quantum computing that exists. Atomic systems are also another approach that has been pursued for a while in the upper left. The idea here is that it's a little bit easier to manipulate atoms than it is to manipulate electrons in terms of the equipment and the spacings. You know, atoms are still quite tiny, but effectively a lot bigger than electrons. And you can put a bunch of atoms in something called a trap, which is what's shown here at the left. And then you can really get very good control over the interaction among the atoms and both, you know, between the atoms and in your environment, and do very precise manipulations of their states. So those are atomic systems. Majorana fermions are an approach that is being pursued by Microsoft and a few others. The general idea is called topological quantum computing. And the problem that people are trying to solve with topological quantum computing is sort of essentially the decoherence problem. It's the fact that, you know, if your quantum state is just encoded in an individual electron spin, and so you have a stray, you know, ray of light that comes in and interacts with that electron spin and changes its state, well, then you've screwed up your computation, and because of the uncertainty principle and the no cloning theorem, you can't just recover it, right? So because error correction is very difficult because of those. So the idea behind Majorana fermions is it's sort of a self-correcting system in that the information, rather than being encoded locally, is actually encoded in these particles that you know, we're only recently observed for the first time, people think. It's sort of these particles that exist in certain strange two-dimensional systems. And they have this very strange property that if you move them around each other in circles, you know, or you sort of braid them together, that actually changes the state of your system. Even if you say you have one of them and then you encircle it completely around the other one, you think naively, well, I just got back to where I started, but in practice, you've actually you've changed the overall state of the system, and therefore you have a way of encoding information in something that is non-local and is more robust against you know, environmental interference than just an individual electron or individual atom. So that's the goal there, but these particles are very, very elusive, only appear at very low temperatures. There's only been some circumstantial evidence that they even exist at all. And you know, trying to actually manipulate them and you know, and make a qubit out of them is still maybe a ways away. Another approach people are pursuing is working with individual photons or individual particles of light. That's another interesting system. I'm not going to say too much about it because I don't know too much about it, but it's something people are pursuing. I'll just say one of the challenges there is actually alluding to a question that was asked earlier. How do you entangle two quantum bits, right? Well, that's one of the challenges with all of these, but with photons in particular, that is actually a big challenge because photons tend not to interact very much with each other. You can think about it, if you just have two flashlight beams and you shine them across each other, well, they'll just shine right through each other, right? They don't, nothing weird happens when you shine two flashlights together, right? So that's, that sort of illustrates why it's hard to entangle photons, because they tend not to interact with each other. And so in order to generate entanglement, you need to be able to get your particles to interact. And so people working on photonic quantum computing have ideas for how to do this with certain materials that kind of harness um, I'm trying to think of the word. They sort of increase the rate of interaction between photons, but it's challenging to do that. So finally, superconducting circuits, they're what we are working on at IBM. People have been working on superconducting qubits for over 2 decades at this point. They're sort of the oddball in this, in that the other ones really are talking about like individual particles or individual atoms. And now here we're talking about a whole macroscopic circuit that you can see with the naked eye. So it's very different from all the others. But as I said, thanks to the beauty of superconductivity, these systems can actually be made to behave in a very simple way, and in a way that sort of gives us the freedom to engineer whatever type of artificial atom that we want. Right? We can change the properties just depending on the design of the circuit, and make things that are easy to work with, have predictable properties, and are easy to scale up, and can be made using available techniques and controlled using a hardware that's just off the shelf. So they've been a really versatile platform, and really easy to work with, and that's helped accelerate their rise. Despite having some challenges, the fact that they are more macroscopic means that there's sort of more stuff interacting there, more issues with things like decoherence, for instance. But there's been a lot of progress in working on making that less of an issue by improving the design and the materials, etc. Just to give a bit of an overview of, there are many different companies and other institutions working on quantum computing now. If you looked at 10 years ago, most of these entities either didn't exist or were not working on quantum. There's been a large increase in interest over the last decade from companies in pursuing all different types of quantum technologies. IBM, as you can see, we're working on superconducting qubits. IBM has been working on quantum information science in general since for about half a century, actually. Basically, as soon as the ideas behind superconducting qubits came out in the 90s, there were already people at IBM that were thinking about quantum information and knew how to make quantum circuits, and said, "Hey, well, let's start making quantum bits." And so that's sort of the history of how IBM has been involved in quantum computing and why we're doing superconducting qubits. Other companies have brought their own expertise to different areas, or been founded by people working in university labs that decided to try to commercialize a particular approach that they were taking. So it's very exciting with all these different approaches being pursued, and sort of a race to see, well, which approach and which company is going to be the first to actually do something useful that you couldn't do with a classical computer. So let me. I liked that little question pause that we took a second ago, a few minutes ago. I want to just figure before I go on a little more, just see if there are any burning questions here. Oh yeah. Sorry, I forgot to expand to slideshow view there a while ago, but I did fix that. I won't forget this time. Any burning questions? Looks like you're not. Okay. All right, I'm gonna press on. So before I launch into superconducting qubits and how those work, I thought I would start with an analogy to sort of help explain where I'm going here. And so if you think about a pendulum, just a regular pendulum, pretending that quantum mechanics doesn't exist, like the sort of pendulum you would encounter in your everyday life, you can imagine it just, if you think about what's the lowest energy state that pendulum can be in, you can just picture it. They're just hanging down and not moving, right? And you know exactly where the bottom of the pendulum is. You know exactly how fast it's going. Well, it's because it's not moving at all. And if you wanted to say excite that pendulum out of its ground state, out of its lowest energy state, you could just pick it up and let it go, and really at any energy you want to put it at, you could put it at. So that's classical pendulum. Now, with a quantum pendulum, there's a problem, and it comes from the uncertainty principle. Right off the bat, if you think about, well, what's the lowest energy state of a quantum pendulum? What's the position? What's the momentum? those are things that you can't measure both of those precisely. It would violate the uncertainty principle. And according to the uncertainty principle, a particle is a quantum object. It obeys quantum mechanics, and it turns out that if you try to measure both its position and its momentum at the same time, well, you can't do it. These are they're called incompatible observables. And so the lowest energy state of a quantum pendulum, therefore, cannot be the state where the pendulum is just sitting at its lowest, sitting completely still right in the center, because that's not a valid quantum state. It's not an allowed state for the system to be in. It has to have some amount of what's called 0-point motion. It's essentially sort of moving around randomly, and it's with some unknown momentum as well. And it turns out that if you want to excite the quantum pendulum out of its ground state, well, there are only certain energies that it is allowed to even be at. The other energies are simply not allowed. They're simply forbidden by the laws of physics. And you can calculate, given the relevant properties, you can calculate what the allowed energies would be. And so this quantum pendulum is certainly a weird object, but there are things that actually behave like this. And the key, you might ask, well, how do I make a quantum pendulum, right? Like what makes a pendulum behave quantum mechanically or classically? It's really about the temperature of the system, relative to, say, the characteristic energy of the pendulum. And if you go down to, so if you go down to very, very low temperatures, temperatures that are very low relative to sort of the energy associated with the motion of the pendulum, then you would find that these quantum effects hold, okay? And so what we're gonna do is we're gonna create a quantum pendulum. We're not gonna create a physical quantum pendulum. It's difficult to do that, although people actually have done that. It's actually really, really cool. People have made these micro-mechanical things. So they're not really pendulums, but they're more like drums, and people have made drums that behave quantum mechanically, which is sort of crazy to imagine, like a physical membrane that can be in sort of a superposition state. But we're not going to do it mechanically. We're going to do it electrically. We're going to have an electrical circuit that behaves sort of the same way as a pendulum. And you think of it much like the oscillator that you would find in a radio. It's the oscillator in a radio. It has a capacitor and an inductor, and those are put together in parallel to make what's called a tank circuit. And by varying the capacitance on that, you can adjust its resonant frequency, and that lets you tune in whatever radio station you want. And so the circuit we're going to make is sort of the, that circuit is the electrical analog of a pendulum. And that is exactly the type of circuit that we're going to use as the basis for our superconducting quantum systems. We're actually going to use sort of a family of devices that resemble that type of device. And in particular, there really are two building blocks that go into our superconducting processors, as we call them. They're what we call superconducting microwave resonators here on the bottom, and those are really just exactly what I just described, except instead of having a discrete inductor and capacitor, it's sort of just this strip of metal. And this strip of metal can have a voltage on it that oscillates, essentially, and with a certain resonant frequency. And so the length of that metal would determine the allowed energies of this quantum microwave resonator. And it turns out that for this type of system, for the quantum resonator, all of the allowed energies are all spaced equally, and they correspond to adding a single photon to the system. So each time if you send in a photon to your resonator and it gets absorbed by the resonator, then that'll take you up one rung of the ladder in terms of the allowed energies that this quantum resonator is allowed to resonate at. But that's not, so that's an important piece of the puzzle, but it's not going to give us a qubit, because for a qubit, we really need a two-level system, something that where we can really just isolate a level that we call 0 and a level that we call 1. And for that, we need to modify the circuit slightly, but only slightly. What we do in that case is, instead of, it's more of what we call a lumped element circuit. So instead of just a strip of metal, it's actually a separate inductor and capacitor. But instead of just a regular inductor, we're going to use something called a Josephson junction, which is, if you look in the diagram, let me annotate. If you look right here, What you're seeing there, I'll show in a slide how we make this thing. It's basically two fingers of aluminum metal, two thin layers of aluminum that are overlapping. And in between them, there's a little bit of aluminum oxide, which is an insulator. And aluminum is a superconductor. And so what this does is it gives us something that behaves a bit like an inductor, but whose inductance depends on the amount of current flowing through it. And what that does, it turns out, and I'm sort of, I don't have time to go into all the detail on this, so I'm keeping it a bit hand wavy. It just takes the energy levels of this system and it makes them so that as you go up in energy, the difference between one energy level and the next changes. Okay, and that gives us the ability then to have a two-level system with a unique energy spacing at the bottom. And we designate those two states as 0 and 1, and those are going to be the basis of our quantum bit. These two lowest energy states of this particular quantum circuit, which is actually called the transmon for reasons I won't get into. So this is a superconducting transmon qubit. It's a zero-resistance junction in parallel with a capacitor, and that plus these resonators gives us everything we need to sort of send in signals and measure the states of the qubits and entangle qubits together, which I won't go into too much detail on how we do it, but I'll go a little bit more in a second. See, there's some messages in the chat. I see one of my the dual mon is something I'm not familiar with. But I think I think I know where that's going. Let me not try to answer that now. I can send you a reference on that. It's how superconducting qubits work. I think I'm sort of getting into that. Hopefully, if there are there any specific questions on any of what I just said? Let me keep going. So just to sort of look at a bigger picture now, we've seen an individual quantum bit, right? We've seen a superconducting microwave resonator. How do we actually put those together to make a quantum bit or a quantum processor, right? So here's a quantum processor. It's actually 5 years old at this point, but the basic principles are the same. You think that actually the newer ones are sort of slightly harder to annotate. So this is a nice simple one. So I still like this one just for explaining things. It's a 4-qubit device from 5 years ago. The qubits are exactly what we just described. They're these capacitors with a Josephson junction in the middle of them. They have a resonant frequency at around 5 gigahertz, and so in order to interact with it, we send in signals at around 5 gigahertz. The anharmonicity, that's the difference between the subsequent energy levels as you go up and higher energies. You don't need to worry about that for today. So we've got 4 qubits, and then we've got resonators of different flavors. There are basically 2 different types of resonators that are on this chip. The first one that you see in the light blue, actually, the ones in the light blue are what we call bus resonators. They essentially provide a coupling from one qubit to its neighboring qubits. And this is sort of the underlying coupling and that lets us entangle them when we want to, right? It doesn't just automatically entangle them all the time, but it lets us apply a certain pulse that will then generate entanglement between the qubits, which I'll come to in a slide or two. So those are the bus resonators. And then the other type of resonators are different colors associated with the color of the qubits. And they're what we call readout resonators. And the idea is, in order to measure the state of the qubit and see if it's 0 or if it's 1, we send in a frequency pulse near the resonant frequency of the readout resonator, and look at the how that tone is transmitted off of the readout resonator, and that lets us know the state of the qubit, because the qubit is coupled to the readout resonator in such a way that it affects its frequency slightly. And so by probing these readout resonators, we can learn the state of the qubit without without coupling the qubit very strongly to the outside world. The readout resonator sort of protects the qubit from the outside world and letting us just measure it in this very careful way. The measurement, of course, will still collapse the state of the qubit. If it's in a superposition and you measure it, you'll still collapse it to 0 and 1. but the presence of the readout resonator sort of lets you make sure that you're only measuring the qubit when you want to be measuring it, and not say all the time. Because if you're measuring it all the time, then you're not going to you won't be able to do any computation because you'll never get into a superposition state. And then finally, everything else you see is just basically metal. There's some holes in the metal that show up as little white dots. Don't worry about the details of that. Just to talk about how do we actually make this thing. So it's on silicon. It's an 8-inch silicon wafer, 8 inches in diameter. And then what we do is we then deposit niobium, which is a superconducting metal, on top of that, about 200 nanometers thick of niobium. And then for the most of the features that you see, we then pattern them using a process called photolithography and then reactive ion etch. And what that does is it lets us define a certain pattern that we then etch, where we pattern of which we etch away the niobium, leaving behind just the metal features that we want in order to create the circuit. So that's for the capacitors and the resonators. Those are all formed with the niobium step. And then the Josephson junction is formed using a special process called a Dolan bridge and e-beam lithography. Essentially what it is you put down essentially a plastic called e-beam resist on top of your chip. And this plastic is actually sensitive to, if you shine a beam of electrons on it, which you can do very, very precisely, and draw a certain pattern on it, it will change the solubility of this plastic in something called the developer. And so then you shine an e-beam in a certain pattern on this plastic, and then you rinse it in the developer, and that causes the plastic to essentially dissolve in those regions. And then that leaves behind something that, a feature that then lets you put this object in what's called an evaporator. And you're going to then heat up aluminum metal. You're going to evaporate. You have a source of aluminum. You heat that up so that it evaporates, and the aluminum then gets deposited onto the surface of your chip. And you do that in 2 steps. The first step you go at one angle, say this way, and then you do it in a second step. And between those 2 steps, you actually oxidize the aluminum layer, and that gives you that right here in the middle. Gives you that aluminum oxide, aluminum sandwich that I talked about that defines the Josephson junction. So that's a complicated process, but hopefully at least you get somewhat of a feel for it. I don't want to dwell on it too much because I want to get to doing some interesting demos. But I just thought I'd give you a sort of a rough flavor for how the fabrication works. It's all done in a clean room on our site here in Yorktown Heights. So how do we actually control these devices once we have made them? I mentioned that the qubits have a resonant frequency around 5 gigahertz. And so what we need to do is we need to send in a pulse of energy at 5 gigahertz. And if you do that, if you send in a pulse of energy at 5 gigahertz, it'll cause the qubit to oscillate. Say you start in the 0 state because that's the lower energy state. It's the ground state of the system. If you just leave it alone, it'll sort of relax down to that lowest energy state. And then you send in your 5 gigahertz tone, and if you just send in pulses of varying lengths and look at the probability of measuring in 0 state as a function of the length that you send in, you'll see if you're at 0 length, then you'll be 100% probability of measuring 0 state because you haven't done anything to it. But then as you increase the length of the pulse that you're sending in, your probability of measuring 0 oscillates back and forth. It oscillates back and forth between 100% and 0%, and that corresponds to the fact that you're oscillating between the 0 state. Here shown again using the block sphere. It's at the north pole of the block sphere, oscillating between the 0 state and the 1 state, and back and forth. But you can apply a pulse of any arbitrary length that you want, of course. And if you apply a pulse that's somewhere halfway in between, then you're leaving the qubit in whatever superposition state that corresponds to on the block sphere. And so there's a term that we use a lot in quantum computing called a pi pulse. A pi pulse is the quantum version of just a NOT gate, right? So classically, if you have a NOT gate, it just flips a classical bit from 0 to 1 or 1 to 0. The pi pulse does the same thing to a qubit, right? And the reason we call it a pi pulse is thanks to this block sphere representation, where it takes you pi radians to go halfway around the sphere, to go from the top to the bottom. And so that's where the pi pulse comes from. So if you do 1 pi pulse, you'll go from 0 to 1, and then if you do a second pi pulse, you'll go from 1 to 0. If you want to put the qubit in a superposition state, you can do a pi over 2 pulse, or any other pulse of intermediate length. So that's how we control single qubits. Now for controlling, probably the hardest part to explain of this whole thing with superconducting circuits is, well, how do you actually entangle them? And it's very subtle, but you can think about it in sort of an abstract way first, and then it might give a little bit of intuition for what's going on. So the entangling gate that we're going to do is called the C0 gate, or the controlled NOT gate. And it's a gate that exists in a classical computer too. Oh, I see how to do the color now. That's cool. Let me use green here. So if you just look at the top part of this table here, get lost the annotation. 1 second. There we go. There. If you look at the top section of this truth table here, this is just the classical behavior of the controlled NOT gate. It's just a gate that says, I have 2 qubits. One of them I'm going to call the control qubit. The other one I'm going to call the target qubit. And if the control qubit is 0, I'm going to leave the target qubit alone. If the control qubit is 1, I'm going to then flip the state of the target qubit. Right. So the initial states are on the left, the final states are on the right. You can see that in the second row there, the control was 1 to start with, the target was 0 to start with. And then after doing this operation, I've now flipped the target to make it also 1, just like the control. So classically, that's pretty straightforward. And now, quantum mechanically, you can ask, well, what happens if I do this on a superposition? And that's this notation here, which I haven't had a chance to go into in a lot of detail, but this is how we write a superposition quantum mechanically. It's sort of, right, alpha and beta are coefficients that are sort of, describe the amplitudes of the 0 and 1 states in our superposition. So we're saying, okay, we're starting the control qubit in a superposition. Target qubit is 0. What's the final state in this case? And it's just take a second to think about it, right? If I'm doing a gate, I'm going to apply some operation to the target qubit, but the operation I apply depends on the state of the control qubit. But the control qubit isn't in a definite classical state; it's in a superposition state. It turns out that this is an example of how you can entangle 2 qubits, because you've created this correlated state where neither of them is in a well-defined 0 or 1, but they're sort of in this state where naively you sort of know classically if you measure one of them and you get 0, well, the other one's also going to be 0, right? And if you measure one of them and get 1, the other one's also going to be 1. But the correlation is actually more fundamental than that, as we'll see when we go over to Qiskit and start doing some examples there. Oh, that's not what I want to do. 1 second, there we go. So let's see how we're doing in time. We're going until 5 o'clock, right? Yeah, I'll take that. So I want to make sure we have time for questions and for doing stuff. So let me skip over some of this. I'll just briefly show. Give her the annotations here. Clear drawings. Just briefly show a little bit on how we send in these control signals. They're sent in with racks of equipment that look like this. These are called arbitrary waveform generators. We're working on trying to improve the scalability of this. This is called a dilution refrigerator. This is where we actually put these quantum systems to make them to get them as cold as they need to be. In order to see these quantum effects, they get down to 10 millikelvin, which is a fraction of a degree above absolute 0. There's a lot of wiring and stuff that goes in there that's very carefully chosen to sort of let our signals in and out without letting interference in. You can see more details of a dilution refrigerator. There's sort of different stages going from top to bottom. It's 40 Kelvin, 3 Kelvin, 0.8 Kelvin, 0.1 Kelvin, 0.01 Kelvin, stepping all the way down. And let me talk a little bit about cloud-based quantum systems, and then we'll dive right into some examples. So, if you wanted in 2015, if you wanted to program a quantum computer, you essentially you had to either work in a lab that had a quantum computer or know someone who did, and you had to know sort of a very low-level language for talking to all those instruments, for sending in the pulses, for reading the measurements, interpreting them. And what we've done in the last 5 years has made it a lot easier. Now you can just go onto our website, quantumcomputing.ibm.com, And you can access our quantum computers over the cloud, and you'll see you can just send things in through the drag and drop interface, and it's very easy. That's the IBM Quantum Experience. I'll skip a little bit over the details of what happens when you send in a system, or send in a job to one of the systems. But if you look at our we have a bunch of these quantum computers online now. We actually have a quantum computation center up in Poughkeepsie that we opened last year. We have a 53 qubit system up there. We have many systems available, some of which are for clients, many of which are available to anyone in the world to use freely. And when we write quantum circuits, we're gonna use something that is what we call the quantum score. It's essentially a very simple way of representing a quantum circuit with a series of operations on each qubit. So each row here represents a different qubit, and then as you go from left to right, you're sort of looking at what's happening as a function of time. And these different boxes represent different types of operations that you can do. And then the one at the very end is representing the measurement operation. So what we're seeing here is that we have a quantum register with 3 different qubits in it, Q0, 1, and 2. We're going to do a series of operations on those, and then we'll do measurements at the end and store the results of those measurements in a classical register. So this is a really good way to learn about quantum circuits. It's very intuitive. There's a drag and drop interface. But as you get to large and more complex circuits, it really becomes unmanageable. And so that is why we invented what we call Qiskit. I'll skip ahead a little bit. Qiskit, for those of you that know Python or programming in general, it's pretty easy to pick up. It gives you a much more powerful way of running things on a quantum computer beyond what you can do with simple drag and drop examples. Not only can you build and run circuits on a quantum computer, but you can also do higher level things like simulations. You can we'll see an example in a little bit of how to study errors and mitigate some of the errors that happen. And ultimately, this is something that can be used to solve real-world problems. Of course, we're not at the point where you can solve anything that you couldn't solve with a classical computer, but you can at least see how a quantum computer could be used to solve certain toy problems. With that, that's basically everything I wanted to cover from here. So let me jump over. I'm going to stop sharing my PowerPoint, and I'm going to share my browser. And if anyone would like to follow along, I'm going to quantum-computing.ibm.com, and we're going to try some things out. Right here. So I hope everyone can see that. So I'm at quantum-computing.ibm.com. I have an account here on the IBM Quantum Experience. And I'll just start here at the dashboard page, sort of showing the first page that you get to when you log in. You can see on the right here, it has a list of all the quantum computers I have access to. And I'm using my account this should look the same as what you would see. I have another account where I have access to all the different devices that we have, but this account just has access to the same ones that are available publicly. And you can see there are several different ones listed there. Let's pull up one called Rome. I happen to that's one of our newer ones. And this just shows you what it looks like. It's actually just 5 qubits connected in a line. And these arrows between the qubits, those represent those bus resonators that I showed you in the diagram of what one of our superconducting processors looks like. They represent the possibility of applying a pulse to entangle 2 qubits together. Oh, actually, you know what? When I was explaining what the CNOT was, I didn't actually talk about physically how we do it. I covered the idea in the abstract. Suffice to say, physically with superconducting qubits, if you have 2 qubits that are coupled by one of these bus resonators, you can apply a pulse that will essentially drive exactly that CNOT operation that we discussed, right? It will do a pi pulse on the target qubit, depending on the state of the control qubit. It's a pretty subtle effect and hard to explain, so I'm not going to go into more detail than that. But hopefully you get the basic idea that where you see qubits that have these arrows between them that are connecting them, what that just means is that you can apply a controlled NOT gate between those 2 qubits. So this is a pretty simple device, just 5 qubits in a line, each of which can be entangled using a controlled NOT gate with its nearest neighbors. You can view more properties of the device. Actually, I'll show later how to view more properties of the device. For now, we'll just see, okay, it's a 5 qubit device, and you can see how they're coupled. And you can see a little bit about the error rates, actually. So, I mentioned that decoherence is a challenge, errors are a challenge. And we actually, every day, we characterize the operations that we can do on the system, both the single qubit gates and the controlled knot entangling gates. We characterize them as far as, well, what are the error rates that we're currently observing. That's the list of devices. If we just want to start off with a simple example, let me pull up the circuit composer, and we can just make a quick circuit to show some things. So please follow along if you're interested. So the first gate I want to start with in the circuit composer is actually the Hadamard gate. And the Hadamard gate is a gate that basically if you start off in the north pole of the Bloch sphere in the 0 state, it's going to put you down on the equator in a superposition state that's known as the plus state, and that'll take you from a state that has a well-defined behavior if you measure it right. If I actually let's just before I put that, let's just look here on the left, and we'll look. If you go over to this bar graph here, it shows you the visualizations. And actually, I'm going to do one more thing. I'm going to simplify this circuit a bit to just have two qubits in the quantum and classical registers. That'll simplify the outputs a bit. Right. So it's going to show us. We're not actually running anything on a quantum computer. We're not doing any measurements, but this is a simple enough system that as we change things, it's going to be sort of calculating or simulating what it would do and showing us what to expect if we were to measure it here. And so what this is saying is that if we were to just measure both of these qubits, they've been prepared in the 0 state for us. We're not doing any operations on them. This 0, 0 here means that we were going to measure both 0 on both of them with 100% probability. So that's not very interesting, right? Now, if I do a Hadamard gate on qubit 0 here, you see now we get something different. Now each of these has in this what's called this state vector view has an amplitude of 0.707. It turns out you need to square that amplitude in order to get probabilities. If I want to see probabilities, I can just select measurement probabilities there. And I see now that I have a 50-50 chance of getting 0, 1 or 0, 0 for the two qubits. And it's a little weird. The bit ordering is such that qubit 0, as shown on the right here, actually corresponds to the rightmost bit in the state vector here. So 0, 1 is referring to the one state, qubit 1 being in the 0 state and qubit 0 being in the 1 state. So I've done a Hadamard that gives me a 50-50 chance of measuring 0 or 1 on this single qubit here, and of course the other qubit just stays 0. So you might think, okay, well I've just made the system behave randomly. But there's an important distinction to be made from a system that's behaving, a system that's in sort of a random state versus a system that is in a definite state but will behave randomly if you measure it. And that is, if I do a second Hadamard now, you can see I'm now back in a state where I get a well-defined answer classically. I get or when I measure it, I'm in a classical state because I get 0 with 100% probability again. And so this shows you that it sort of gives you a feel for superposition. That I've put this, when I did that first Hadamard, I put the qubit in a superposition state. If I then measured it, I got a random outcome, but it was still in a definite state. If I then did a subsequent manipulation to it, I could get it back in a known state. So that's just a very simple example of superposition. Now for entanglement, we can again also play around with seeing entanglement using controlled knot gates. If I get rid of both of these Hadamards. If I just put a controlled knot gate here, right, and so this notation, by the way, this small circle means I'm using Q0 on the top here as the control qubit, and the plus on the bottom means I'm using Q1 as the target qubit. So I've just done a controlled knot with Q0 as the target qubit, and I haven't, but I didn't do anything to qubit 0 to start with, so nothing happened, right? Because the control qubit was 0, so it was basically nothing. So that's fine. So another thing I could do just to sort of see the classical behavior of this circuit, if I put an X gate, which is equivalent to a pi pulse, it rotates. The X gate would take the Q0 from 0 to 1. And now I'm starting with I have the control qubit in the 1 state. I then do my controlled knot gate, and now it's also going to flip the target qubit to 1. So now they end up both being 1, right? But now the most interesting case is, well, what if I put a Hadamard gate before my controlled knot gate? Oops, wrong side. There we go. And if I put the Hadamard gate there, you see now I end up getting 0, 0 or 1, 1, each with 50% probability, sort of as I discussed. And this is not too surprising, but there's actually something really really interesting you can do to take it a little bit further. And that is, you can think about when we measure a qubit, right? We sort of, naively, when we talk about measuring a qubit, we're talking about asking it the question, are you 0 or are you 1, right? That's what our measurement can do. Our measurement can tell us if the qubit is 0 or 1. But say we want to know something different. Say we want to know if we're in a superposition state, but we want to know, well, which superposition state are we in? You know, if you picture that block sphere, let's say imagine you're on the equator of the block sphere, but you want to know where on the equator you are. That's represented by, or that represents what's called the phase between the 0 and the 1 states. And so the superposition, you know, you recall it had those amplitudes alpha and beta. But if beta is negative or imaginary, then that corresponds to there being a different phase of your superposition. And that's something that you know, you won't be sensitive to just with that naive measurement of are you 0 or are you 1, right? Because regardless of where you are on the equator of the block sphere, if you just ask the qubit, are you 0 or are you 1? Well, you'll get 0 and 1 with 50-50 probability, but it won't tell you any information about where the qubit was on the equator. That information was simply lost as part of doing the measurement. This gets back to the uncertainty principle, the fact that it's hard to do error correction, the no cloning theorem, and all of that. But if you say you want to actually put a qubit in a state on the equator of the block sphere, and then you want to know, well, which state on the equator was it? Was it the one at you know, say, if you think about the equator, you know, equivalent to being on the globe, you know, is it in Hawaii or is it in Africa, right? Where on the equator which superposition state does this correspond to? There's a way to do that, and it's by asking the qubit a different question, effectively. And so what you're going to do is instead of just doing the usual measurement at the end, it turns out that simply applying another Hadamard gate is equivalent to asking it a different question. And so this is an experiment we already saw. It's 2 Hadamards, but we're going to interpret it a different way now. And it's going to be important for what comes next. And so the other way we can interpret this experiment, instead of saying, okay, well, I put the qubit in a superposition and then I took it back out of a superposition and I'm back where I started, I'm going to say this second Hadamard gate here was effectively changing the question that I asked the qubit. It effectively allowed me to ask the qubit the question, instead of are you 0, are you 1, I asked the qubit, you know, are you Hawaii or are you Africa, right? Or in terms of the actual terms that we use to represent these superposition states, are you in the plus state or the minus state? Those are the names for the 2 superposition states at opposite ends of the x-axis on the equator of the block sphere. And if you think about how that works, you know, if the qubit is in the plus state, which it was here, then when you do the Hadamard gate, it's going to take you back up to the 0 state. And so you effectively, you'll get a 0 if the qubit was in the plus state. And but if you had done a z operation, which is a rotation around the z-axis and puts you at the opposite, puts you in the minus state at the other side of the equator, if you put that there, then you'll see that you always get this 0 and 1. We're now, so this, again, the 1 here at the end is the one corresponding to Q0. And we're getting that with 100% probability. And that's because if you are in the minus state, and then you do a Hadamard gate, then you get, you'll get 1 with 100% probability. And so we've essentially mapped the plus and minus states over onto the 0 and 1 states, and effectively changing the question that we're asking the qubit. We're still getting 0 and 1 at the end of the day, but we're able to interpret it differently. We know that if we got 0, it means we were in the plus state, and if we got 1, it means we were in the minus state. Okay, so that's what adding this Hadamard will do. And now we can do something cool. If we come back to our CNOT example, we can, so recall, in the CNOT case, we did, if we just did Hadamard and then CNOT to prepare this entangled state, we get 0, 0 or 1, 1 with 50-50 probability. If we then actually measure both of these qubits in a different basis, though, and we ask them a different question, instead of asking, are you 0 or are you 1, we ask the other question of, are you plus or are you minus? You can see we still get 0, 0 and 1, 1, right? And this is kind of interesting. Naively, it's not, you wouldn't necessarily expect this because you're now asking the qubits a totally different question, right? It was sort of obvious why, based on the setup of the experiment, you know, classically you'd think, okay, if they're either both going to be 0 or both going to be 1. But now it turns out that if you, instead of asking them, are you 0 or are you both 1, if you ask them both, are you plus or are you minus, they still give you the same answer. And this shows that the correlation that comes with entanglement is really a much more subtle and profound thing than just sort of what you'd expect from a classically correlated system where, you know, if qubit 1 is 0, then qubit 2 is also 0. It's really a fundamental property of the 2-qubit system. I had wanted to also get to an example involving Qiskit and showing showing a little bit about decoherence. Maybe I'll just quickly in like 2 minutes just sort of walk through a little bit about Qiskit and what that looks like, just to give you a sense, a flavor for it, and then I'll take questions in maybe 3-4 minutes. So that's sort of how we can use the composer, how we can demonstrate some basic stuff about superposition, entanglement. Now jumping over to programming, I know not all of you are programming whizzes, but I encourage you to check it out if you're interested. It's really pretty easy to get going with what are called Jupyter notebooks, and we provide a lot of them for you within the IBM Quantum Experience platform. If you click on the Qiskit notebooks button there are a bunch of tutorials, and you can just sort of step through them. Here's one that I'm just sort of writing as I go. This first cell basically has a bunch of commands that load things and sort of get you started with some useful tools. One of which is a list of all the backends that I have access to. You know, this is essentially the same thing that I saw in that dashboard page. You know, the list of all the systems that I can access. And in particular, if I want to work with a particular one of them, I'll pick London actually, because I think that wasn't very busy. So I'll say London equals provider.get backend IBM Q London. And then if I just type London and hit enter, it gives me another interface to explore the different properties of this backend, which it'll take a second to load here. You can see the star there means it's running, and okay, now it finished. And you can see I can see all sorts of different properties about this device. I can see how many qubits it has. I can see how many jobs are pending. I can see how many shots I can run, how many times I can repeat the experiment. I can see more details about the individual qubits, what their frequencies are. As I mentioned, they're all around 5 gigahertz. I can see what their coherence times are. The coherence time is a measure of, you know, back to this idea of, you know, I mentioned decoherence, right? If you put the system in a known state and just leave it alone, eventually it'll get scrambled due to random interactions. That's decoherence. They're different, T1 and T2 represent different time scales for decoherence to happen. You can see they're in the tens of microseconds range. I can see the errors on the single qubit gates, errors on the readout, errors on multi-qubit gates. I can see sort of a map of the errors, and I can even see a list of jobs that I've run on that device. So that's just an overview of that device. And then I won't go into detail on here because there are a lot of tutorials on how to do it. But if you actually want to run something on one of the devices, you can then step through and use commands to actually just do exactly what we did here, except just using using Python, using the language of Qiskit, and with the ability to do more advanced things like write functions and write loops and use conditional logic and all sorts of things to make your programs more sophisticated. And just to close with walking through one more example of that, so you wanted to actually measure the coherence times of some of those individual qubits. Well, there's a very simple way to do that. You prepare a state and then measure it, and then repeat this experiment though, and wait different amounts of time between when you prepare the state and when you measure it, and just look at how the probability of still being in that desired state changes as a function of the wait time. And so this here is a tutorial notebook. Actually, if I want to show you how to load it. Let me if I just go back to the Qiskit notebooks page. So if you click Qiskit notebooks, you'll get to something that looks like this. And then if you just click on, this one's actually under advanced, but there are all these different notebooks you can click on and step through. If you click on advanced and you click Ignis, and then you click on, this one's actually relaxation and decoherence. As I showed, I think quickly, Ignis is the module of Qiskit that lets you do sort of work with studying errors, trying to mitigate errors. And so this particular notebook lives in that module. But here it is. It basically starts off with some, importing some features from Qiskit. And then there's a section here that generates the circuits for actually running these experiments. Essentially do a pi pulse and then wait some amount of time and then measure. There's a section here that then lets you run the experiment on a device. In this case, it doesn't use a real device, it uses a quantum simulator. And then finally, it analyzes the results and makes some plots. And so you can see typical behavior here. If you start with a pi pulse to prepare the qubit in the one state, and then you look as a function of time, function of that wait time of how that population decays, you can see that it decreases, and it decreases exponentially. And this is an example of decoherence and how you can measure it using Qiskit. In principle, if you'd wanted to do this using the drag and drop interface, you could do it. You could just, you're basically, the ID here is an identity gate, and if you just insert a whole bunch of identity gates, it'll let you, wait, wait some amount of time. But you'd have to, insert like thousands of identity gates, and so it'd be a bit tedious to run this sort of thing. With Qiskit, with Qiskit and with the functions provided by the Ignis module in particular, it's a relatively small number of lines of code to run this whole experiment and generate all the plots. So, if you're interested in programming quantum computers, I encourage you to check out Ignis and check out, in particular, the tutorial notebooks that you can access through the website. Here is a good way to get started. So, let's see. That's basically everything I wanted to cover. Sorry, I went a little longer than I wanted. You guys asked some good questions in the meantime, but I want to definitely make sure we have time for questions now. So, there we go. It is a shame I skipped a few slides. Yeah, I can send you this deck certainly if you'd like. Let me go back up here. How many users do we have in which country? Yeah, there are people all around the world using Qiskit, using the IBM Quantum Experience. One of my favorite stories is that within a few days after we launched it in 2016, someone used it from Antarctica already. So we have users on all 7 continents. And yeah, I think I don't personally have the data, and I don't know if I've seen any reports detailing country by country. I've learned that it's actually it's a little bit hard to tell because it turns out a lot of people connect through VPN services or things that obscure the country that people are connecting from. For a while, we thought that there were just a surprising number of people in the Netherlands that were using it, but it turns out the Netherlands actually is just for a large host of VPN services for some reason. So anyway, there is some data on that. I don't personally have it, but I know that people are using it all around the world. There's actually a fun animation that we have that, and so I'll make a note. I mentioned I'll share the slides. I'll include in it this animation showing jobs being run as a function of time from different spots around the world, so you can see that. What is the compiler used for Qiskit? Yeah, that's a great topic and a topic that I could again spend a whole hour alone talking about. The idea of how do you take a quantum circuit and compile it into a language that a quantum computer can understand, right? With the drag and drop interface, you say, I want to do a Hadamard, I want to do a CNOT, I want to do a measurement, or the same thing in Qiskit. But your quantum computer at the end of the day wants to see a certain set of microwave pulses, right? And so how do you translate from this high level language of quantum circuits to the low level language of the quantum device? And how do you do that optimally, right? How do you make sure that you are doing it as efficiently as possible? You're not doing unnecessary operations that are going to slow down the circuit or cause errors. Yeah, it's a really interesting problem, and there's actually a lot of research going on into how to do that. It's a big part of Qiskit, specifically in the Qiskit Terra module. It's called the transpiler actually, because what it does, what Qiskit does, it doesn't really compile circuits in the sense of going from a higher level language to a lower level language within Qiskit. It really, all of the circuits that it works with can be represented in this same format, which is called a chasm. It's sort of a list of, actually I can show you what a chasm looks like. If I go to my circuit composer view, and I'm still sharing here, and I just click on this thing that looks like a code there, I can see this is on the left there is the chasm code that corresponds to the circuit that I've drawn here, right? See, H is the Hadamard, CX is the controlled knot, et cetera. So that's chasm right there. And anything that you can do within Qiskit, ultimately, it starts off as being representable as a chasm, and it ends up as being representable by a chasm. And a chasm is actually what gets sent to the backend for further processing. So the backend actually knows how to interpret things that look like a chasm, but it has only certain allowed operations that it can do, given the restrictions that that it has. For instance, I showed you Rome, showing that only certain nearest neighbors could be entangled with each other. Well, say when you're running a quantum circuit, you don't necessarily want to have to worry about the physical layout of the device and which qubits can be coupled directly to which other qubits with CNOTs. You just want to write a quantum circuit and you want it to run. And so part of what the compiler does is try to figure out how to how do I do that? How do I translate what the user requested into something that the device can actually run, so that that chasm that's being set to the device is one that it actually knows how to run. So yes, anyway, the compiler, it's part of Qiskit. Qiskit is open source. It's github.com/Qiskit, and for instance, the compiler lives within Qiskit Terra, and it's Qiskit Terra, Qiskit, and then there it is, right? It's right there. You can play with it. You can contribute to it. You can do whatever you want with it. It's a big active project. So another question, I'm interested in quantum computing, but I know almost nothing about it. What should I do to get started? Well, I hope this was a good start. I hope this sort of helped give you some ideas about the different components. I think that's definitely one of the challenges people face in trying to get started in quantum computing. There are so many different parts to it, right? There's the sort of the side of the algorithms and in the theory behind it. There's trying to figure out what to actually do with it. What are useful applications of it? What are the devices? How do we make devices? How do we operate them? How do we make them better? And so I think it sort of depends on where you see yourself fitting in. Are your interests lie more in terms of the actual hardware? Do you want to make stuff, or do you want to write code? Do you want to write code that's sort of high level code that's trying to optimize running an algorithm? Do you want to write low-level code that's trying to optimize an individual operation running on a quantum bit? There are lots of different entry points, and I think a good starting point is just familiarize yourself with the different parts of it. There's some if you certainly are lots of resources out there for getting started. I can include some in maybe as a final slide. I'll put that too in the slides that I send out. I'll include a slide at the end with just some more resources for getting started. I'm as far as I know, I can send the slides in a way that will be accessible to you. Let me see what else. What is the equivalent? What does the if gate do? What is the equivalent of it? Qiskit equivalent of it. Yes. So this was sent to me privately, so not everyone saw it. But there was a question about the if gate. So yeah, the if gate that you see in the Qiskit circuit composer is it's a little weird. It's something that is not actually implemented on our real devices yet. It would essentially let you measure a single qubit and then change what you're doing to other qubits depending on the result of that. So it's a little bit different. It's a little bit like the CNOT in the sense that the CNOT is often phrased in the sense of, if the control is 1, then measure the target. Right, but the if gate here is a classical gate. It's not doing the quantum CNOT. It's actually measuring the control qubit, and then if the state of the or measuring the state of one qubit, and then if the state of that qubit is 0 or 1, then do some action, and it can be some arbitrary action. So that's what this if gate is doing. It's a classical operation that requires measurement of part of the device and then feedback based on that. What compiler? Yeah, there's a question about the compiler used to process chasm. Again, the compiler, I think hopefully I answered that, showing it's within Qiskit. You can find more documentation on it within GitHub or at qiskit.org. There's an interesting question on transferring quantum information through quantum circuits. So yeah, quantum computation is a whole other topic, and getting back to the how do I get started part of it. There's I focused on quantum computation, right? But the whole field of quantum information also includes quantum sensing, quantum communication, and there's a lot to explore there too. So quantum communication is something that actually, in principle, provides a provably secure way of sending information. It requires some of the same building blocks as quantum computing, but applied in different ways, and is something that people are working on. It's more about, it's not guaranteeing that well, it provides you a way to guarantee that information cannot be intercepted by a third party and decoded. It's not something that's being used in practice much yet anywhere, but in principle is something that seems very interesting and people are looking to explore in the future. Okay, any last questions? I think we're basically up on time. I think I did my best to try to address all the questions that came through. We'll get the slides out to everyone. Thanks for your good questions throughout. And I guess that'll do it. I hope everyone enjoyed and got something out of it.
Yeah, everyone, thank you, Doug, for hosting this, and thanks everyone for coming. We really appreciate all of you trying to come and get your introduction to quantum computing. If you want to continue learning, we're having our next workshop a week from today on quantum cryptography, which is more what does quantum computing actually do. And you can follow us on all of our social medias, our LinkedIn, Twitter, Instagram, to get updates about more workshops and events like that. Okay, thank you everyone for coming. Bye.